Hello, George. Now,
Hi.
George, we've been talking about other rotaries here today. We've been talking about the water-cooled one, the road bike and the race bike.
Yeah.
Now, you're the only guy here that's got an air-cooled one, and I know we've been chatting, this is a bit special.
Yeah.
And you spent a lot of time building something there's only a one-off of.
Yeah.
So, can you, in your own words, tell me some of the things that you've done to it? You probably won't be able to tell me all in the time.
No.
But it is an amazing machine.
Yeah.
So, in your own words, George.
Basically, what we started with was an old IP2 police bike.
Okay.
Okay, and research showed that mainly the rotary engine was held back by its gearbox design because it used a very old-fashioned gearbox in order to do that. So I had an idea. I had thought, well, what if we could actually get a modern gearbox behind this bike, which brought about a lot of problems. Number one, the engine is going to be rotating the wrong way. So the first thing I had to sort out was to reverse the drive.
Direction.
Yeah, because we want all modern gearboxes are driven with gear. All modern gearboxes are driven with a clutch, which has a gear drive, and that automatically reverses the direction going in the gearbox. Whereas the old Norton engine uses a traditional train drive, and therefore the clutch rotates the same direction as the engine. So what I did is I put in an idler shaft, created a chain drive to the idler shaft, and married the sprocket on the idler shaft to a gear, which in turn drives the gear on the clutch.
Which is a hell of a lot of work.
Absolutely.
A lot of work.
Absolutely.
The reason why you've changed gearbox is because the performance that you're getting from this engine, it couldn't put up with the torque, the stresses
Absolutely.
that you're producing from this engine.
Yeah.
As now it's tuned.
It wasn't until they went to the F1 that they really got a proper gearbox for these bikes. Fundamentally, the air-cooled and the Commanders, which are a water-cooled engine, use an old modified T140 gearbox, 5-speed gearbox, which was okay for about 50-60 horsepower. But in standard form, this air-cooled engine produces 85 horsepower, roughly delivering around about 60 odd foot-pounds of torque, which in the mid-80s was quite something. So therefore, the poor old T140 gearbox that it was strapped to had a really tough job to deal with it. And basically, you've got a very old style gearbox, it's quite clunky, and my thoughts were, if you gave this engine the gearbox it deserved, then you can release not necessarily more power, but you can release, you can use the power that's being produced. I'm not going to make any more engine power, but I can actually make better use of it.
To use what you got to a better
Yeah, absolutely.
degree. So, because we're air-cooled, is there a big difference between the performance of the water-cooled against the air-cooled? And
no, they
this
raced.
is where it all started, wasn't it?
Yeah, absolutely. I mean, the first race bikes were air-cooled.
Yeah.
They then, as soon as the Commander came online, they went to water-cooled, which of course is better because you've got more control over the engine casings, you've got more control over the engine temperature. Fundamentally, one of the biggest problems with rotary engines is heat. They fire so many times when they're running, is that you've got a constant amount of explosions taking place in the rotor chamber, which causes a phenomenal amount of heat.
Because this is far more than like a two-stroke, it's firing...
Absolutely. Well, we get 2 firings every rotation of the crank, but whilst one rotor face is firing, another rotor face is ready, filling with charge, ready to compress and fire.
Yeah.
So that's why. And to give you an idea of this temperature, this here on the end of the exhaust looks like I've set about it with a blowtorch. That's some 3 feet away from where it exits the engine, and that does it all by itself.
That's quite
incredible. That's stainless steel. So you can only run stainless steel systems on these bikes. Anything else it won't cope, or better than stainless, should I say.
So we're running 6-speed gearbox.
This has got to be a gearbox in it from a GSXR 750. So I managed to reverse the direction. The next thing I did was I took a scrap GSXR engine and cut it down so that I could basically separate the gearbox from the rest of the engine. I then did a reverse engineering exercise, making note of all the positions of the shafts, the bearings, the selector drum, all the parts needed to make the gearbox work. I then put those onto a CAD drawing and designed a bespoke casing to go around that gearbox, in effect making it like a pre-unit type arrangement.
A lot of people would say, you can't do this, but you proved people, probably they said, you could never do all that work, but you've done an incredible job on this.
Yeah.
The man hours you put into this.
Absolutely, there were questions at times where I was slightly mad, and was it going to be worth it? But overall, it's not just about the gearbox. It's about what you've now done is to move the engine of the bike forward in years. Production was ceased on these bikes in '93. With the F1, they were really only just touching the surface of what we would call modern motorcycles today. And then the rug was pulled out from under their feet, and as often happens with British manufacturers at that time, they ran out of money.
Can we just talk about the carburation? Because I see under the tape, we've already looked with a picture, we've seen on the camera an SU.
Yes.
Carburetors.
Yeah.
So this is something that you've designed yourself?
No, well the SUs are the standard carburetor.
But they were used.
Yeah, they are the
SUs
standard carburettor. They're a modified SU. They don't have a butterfly in them.
They still have the dash pot, don't they?
They still have the dash pot. The reason that the SU works very, very well with the rotary engine is that because of all this extra heat that we create, it does affect the carburetors. All right. Now the SU does a very clever trick. In the float bowl of the SU is a lever mechanism that has a bimetallic strip in it. And as the carburetor warms up, or the airflow warms up going through the carburetor, the bimetallic strip lifts the main jet, weakening the mixture, bringing it correct to the conditions of the engine and what's required at the time.
Really clever.
So it really suits it. Also, the dashpot system can cope well, or much better, with the pulsing of the rotary engine, which is quite unique as opposed to a traditional piston engine. And I always think to myself, what was the look on the technicians at SU when Norton walked in there and said, we need a carburettor for our rotary engine and it needs to do all these things. A traditional setup, which this one is, uses the carburettor vacuum to draw air through the rotors to internally cool them. So fundamentally, the carburetors are having to deal with warm, oily air. And
as we know, because it runs a bit like a two-stroke, doesn't it?
Well, yeah, but it uses the carburetor because the rotor is cooled internally, which was the great thing that Norton came up with to improve the performance from when Triumph were looking at it and BSA before that. You had to draw the air through somehow. So the decision was made was to use the suck of the carburetors to do that. But any carburetor manufacturer will tell you the last thing you want to do is give it warm, oily air. It's the wrong thing.
Yeah.
But it works on the rotary, and we're still producing 85 horsepower.
Because oily air, you would imagine, by pilot jets and things like that.
Absolutely, but the SU doesn't have pilot jets.
No.
It just has a single main jet, so it can cope with it.
Yeah.
When they produced the race bikes, the first step they did was to make the carburetors free breathe. So they used another system, which is the extractor exhaust system, which you'll have seen on the race bike. That allows the carburetors to free breathe. If you do that and nothing else, you will get a 20% increase in power.
It's incredible. Just talking about the chassis and the front forks, the wheel assembly, these aren't standard, are they?
No, not really. Basically, it came about because if you're going to make basically a sports bike type of power unit, we want something that's a sports bike chassis to put it in. And I stumbled upon the Aprilia chassis by pure accident whilst I was repairing an Aprilia Futura, which is like the Aprilia mill. And I looked at the chassis, and I had my rotary project I was working on at the time, took a few measurements and thought they're just made for each other.
Because anyone would look at this and they would think that was part and parcel of the same
Absolutely.
bike in the beginning.
Absolutely.
It fits there so well.
Absolutely. The reason being is that the V-twin engine used by Aprilia, you need a narrow beam frame. You don't, on 4-cylinder ones, you've got very wide beam at the top, the distance between the two beams. But a rotary hangs under the frame.
Yeah.
It doesn't go in the frame. So you don't need a very big space. You only need enough space for carburation and various pieces
This
like
reminds me of a Scott in a way, because the engine on a Scott is held underneath. The reason I say that, we've been working on a Scott, and it has that similarity about it.
Yeah, and in effect, the engine is part of the structure of the chassis in this case. It becomes a structural member. So it's linking from here to the top. So that was by pure chance that happened. Of course, it being Aprilia, it left open. It's a perfect sports chassis, and Aprilia, like lots of other manufacturers, they build off of a platform. So the Aprilia mill led to the development of Futura, which is the sports touring version.
Spot it on.
It then led on to the Turuno.
Yeah.
It then led on to the Falco. So really what I did was sort of pick bits, one might say. So we're building a sports bike, so I thought it would be rather cool if we had a set of O-lings up front.
It's got to have, isn't it, really?
Absolutely. So those are basically off of a R-Series first generation Aprilia mill. All right. The top yoke is a billet machine one which I made, but the bottom yoke is a standard Aprilia one. Well, the forks are from the Aprilia mill R-Series. The wheels are actually from a Triumph Daytona.
Right, thank you.
I wanted a 3-spoke wheel. The Millie ones are multi-spoked, and I wanted something a bit older, traditional looking, one might say. And they fit in there pretty well. There was just a small adjustment to move the discs in a few millimetres. The diameter of disc used on the Daytona matches the diameter of disc that was used on the mill. So they fit up nicely with the Brembo brakes.
It does look stock. It does. It doesn't look like anything that's aftermarket. It all looks absolutely spot on.
Well, yeah.
So the back end, we're looking at the back wheel swing arm.
Okay.
That's a prettier swing arm, obviously.
It is, but this is a first generation frame, and this is a second generation swinging arm.
Right.
I kind of thought that looked cooler. And all I'd had to do, again, manufacturers are quite lazy, and I play upon that. If you're Aprilia and you want to make a second generation bike, you don't want to change all the geometry.
That's going to be the same, isn't it?
You want to keep it the same.
Yeah.
I merely had to machine one of the central spaces on the swinging arm down by 2 millimetres to make the second gen
That's
fit
all.
straight in. And the shock position is exactly the same. Again, Triumph rear wheel, but I didn't like the cush drive arrangement. It wasn't in quite the right place to get the alignment through, but I actually found, with a bit of modifications, that I took the cush drive and final drive sprocket mount from a Honda VTR Firestorm. And with a little bit of tweaking, that gave me a fit on there. These are actually also Honda Firestorm, because Honda make good kit and they tend to make their silencers from stainless steel, just a dob. Pete Weller, PW Engineering, modified those to put the different nozzles on it, which gives it the nice rotary howl.
It's an amazing bike. I think we've covered most of it. I think looking at this bike, first impression is like beautiful bike, but when you talk about what you've done to it, it's such a work of art.
Yeah, is your brain hurting yet?
It is. It's overloaded, but amazing. And you've done this yourself, so you're a very capable engineer. And you know, there's not many people who can do this sort of thing.
Yeah, I'm still married as well, which is quite amazing.
And you've got kids as well.
Yeah, absolutely.
Yeah, no, that's brilliant. It's really clever.
What we might call a busy man. Yeah.
Well, George, I really appreciate chatting to you about your bike, and it's been a pleasure.
It's been good.
Thank you very much.
Thank you. Thank you.